So this is what we have seen. I guess this is the summary of everything we have seen about gradient descent so far, stochastic gradient descent so far. So we have f of x, which is the expected value of another function, capital F of x and zeta, and then the assumption is that I have an unbiased estimate of gradient. I don't know the exact gradient, I just have access to an unbiased estimate of that. And just to make sure, following essentially Robbins and Monroe paper, just to make sure that xt can converge to x star. The x star is the optimal of f of x. We impose some constraints on the step size alpha t. So it says that alpha t should go to 0, something that we didn't do when we were playing with gradient descent. Summation of alpha t goes to infinity, and then this one says a square of this thing is bounded. And for that one, we said, a natural choice that satisfies these properties is alpha t d over t to the gamma, where gamma is between 0.5 and 1. Then we did the analysis for the mean square error of the estimates. We are hoping that expected value of xt minus x star goes to 0. And eventually, we got this iteration for the mean square error. And then we argued that, if beta bt we can be upper bounded by this type of, by this term, right? If, for example, I choose alpha t here, so bt is going to be upper bounded by this thing. That's the argument I gave last time, a heuristic argument. And then it says that if alpha t is equal to this one, you get something like this expression. So there are a few points, few points that we should emphasize here. The first one is that the convergence rate is much lower than the convergence rate of gradient descent. So convergence rate of gradient descent was something like L over mu minus 1, L over mu plus 1 to the power of t. Or in this case, it's actually power of 2t. But now here we have reduced it, so this is like a geometric convergence, but here we have polynomial convergence or sublinear convergence. So that's the first thing. Gradient descent is much faster than SGD, a stochastic gradient descent. So that's something we should emphasize, but it's not very surprising, right? Given that our estimates of the gradient is very noisy, we shouldn't expect to be as good as the gradient descent. So that's a natural thing to happen. The second thing that we should emphasize here, at least among all the step sizes that I've chosen here, it seems that the best convergence comes out of alpha gamma equal to 1. So the best convergence rate is bt less than, let's say, cmd mu over t. So I have to set gamma equal to 1 here, and then among the step sizes I checked, this is the best thing I can get. So this is the summary of everything we have seen so far. Now let's ask more interesting questions about the stochastic gradient descent. So the first question, again, as before, when we have a theoretical analysis, is that, is our analysis sharp enough? And if you consider the simple quadratic example that I gave you before, the one that the function was f of x, expected value of x plus zeta squared, you can easily see that most of these inequalities are exact equalities. So you can make them equalities. And so the type of analysis that I've given is more or less sharp. So you can do better than this with the analysis. So the answer here is yes. So the second question is, of course, about the optimality, right? So can we improve the convergence rate with whatever means? If you want to change the step size, or if you want to change the algorithm, is this algorithm, is SGD optimal based on the oracle information, on the first order oracle? So this is the type of question that we asked about gradient descent. We are asking the same question, right? So if I have first order information, first order oracle information, can I get better rate, better convergence compared to SGD? And that is the question that I would like to answer now. So this is an interesting question. And I guess if back in around 1950, you would ask this question from optimization and statisticians, they would give you completely different answers, right? So we talked about gradient descent, right? And every time we think about something that is related to gradient descent, we have this picture in mind, right, that I showed you before. This is the picture I showed you before, the ellipsoids of X transpose AX. And everything that is related to a stochastic gradient descent, okay, we always remember this zigzagging picture that we had for gradient descent. And now you can imagine that if something is even a stochastic, it's going to be even worse than gradient descent. So we would expect that, if I average the gradients in gradient descent, it would be better. That was the idea of heavy ball method. And in here, you are saying that, oh, if I average the gradients, not only the direction is going to get fixed, but also the noise that I have added to gradient, this independent noise that I had in the stochastic gradient, they're going to average out, and maybe the noise even reduces, right? So if you are an optimization person, so your answer, I think the natural answer that you would give to this problem, let's say in 1950 to 1960 type, right? So now, I guess optimization people know the answer. But if you were in 1950, you would probably answer, your answer would be SGD is suboptimal. So I have to do heavy ball method and then take the average of the gradient somehow and get a better algorithm, right? And that's exactly what people tried to do back in those days. Too, but I'm going to get to these directions a little bit later. But if you ask this question from a statistician, you would get a very, very different answer from the statisticians, right? So to them, they feel like this is optimal. And I'm going to tell you why, right? So the idea is the following, right? Suppose that I have some random numbers, let's say y1 to yn from a Gaussian, right, IAD Gaussian, and then I want to estimate the parameter theta. This is the most classical problem in the statistics, right? So what would you do? Essentially, everyone hopefully will agree that if I do maximum likelihood, if I do basic averaging, this is the estimate that I'm going to get for theta, right? This is going to be my theta hat. And then if you think about this estimate, you will see that it's very easy to see that, theta hat minus theta squared is going to be 1 over n, right? So, and then what you can even intuitively agree with me, and then there are lots of proofs for it in the statistics literature, you would say that there is no way to do better than this in estimating theta, right? There are many reasons. There are many approaches to deal with this problem. But this 1 over n rate in a statistics is very fundamental, right? If you're talking about calculating mean square errors, this 1 over n rate is a very fundamental lower bound that we can't beat. Everyone is with me so far? Makes sense, everything? Now, if you look at the stochastic gradient descent, you see that, after t iterations, you are getting to 1 over t rate 2, right? So this is I think, okay, essentially this is what we have here, right? Gamma is equal to 1, so we are getting to 1 over t. So essentially, a statistician would say, you know what, you are trying to estimate the minimum argmin of this function. This is x star, but how many observations do you have about x star? So you have, let's say, t gradients, right? So let's say even these t gradients were giving you exact information about x star, right? You still have t more or less independent samples about x star. So the best thing that you can hope to get for x star is probably 1 over t, the same as what we have here. And I'm going to clarify this argument in a second. But a statistician would probably argue that, from here, the statistician would say SGD achieves optimal performance. And in fact, given that statisticians were working on a stochastic gradient from 50 to 60, you see that all the results were in that direction to prove that SGD is optimal, and we can't beat SGD. So now let me give you an example so that you see why this argument really is correct and why it makes sense. And then I'm gonna talk about the other results that we have. So what is the idea here? I want to show you that essentially this 1 over t rate makes perfect sense when it comes to SGD. These type of algorithms that are using first order information. Okay, so what am I going to do? I assume that I have this model. So again, I'm going to choose a very simple function. So example, to clarify the lower bound. Clarifying lower bound. Okay? So I'm going to define my function this way. F of x is equal to expected value of x plus zt squared. That is the function that we saw before. But now my zt, let's say, is IID Gaussian with mean theta and 1. Everyone is with me? So you can easily take a derivative of this thing, right? So it's going to be x squared minus 2x expected value of zt plus expected value of zt squared. If you take the derivative, you will easily see that, the optimal value x star is expected value of zt, which is equal to theta. So eventually, what your stochastic gradient descent is going to go to is the mean of this noise, right? That's the optimal point for your stochastic gradient descent. Now let's think about what a stochastic gradient descent does, right? So the stochastic gradient descent is going to do it this way. It says that, so what is, okay, let me just put a 1/2 here too. So just, okay, x star, I'm going to write it here, x star is equal to theta. At the first iteration, a stochastic gradient descent takes your, let's say, estimate x1, draws a random noise, Gaussian noise, independent from this distribution, adds it to it, and gives it to you, right? So this is the first information that you get from your oracle. Okay, you somehow figure out what x2 is. You go to x2, then again go to the oracle to get information about the gradient, and then it will give you x2 plus z2. And again draws another independent noise from the Gaussian and then adds it, so forth, and so on and so forth, until it gets to xt plus zt. So now what you can see is that, the final information that you have here is not in x1, right, or x2. It's really in zeta1, zeta2, because they are coming from your distribution, right? So essentially, the information you have about theta at the end of the day is the same as the information that zeta 1, zeta 2, zeta t are giving to you. Okay? And from this information, now you want to estimate theta. What can you do? Again, you're back in the Gaussian setting, right? That you have IID information from Gaussian. So the mean square error, the best thing that you can hope for, is kind of averaging everything. That is what the best algorithm is going to do. And when you average everything, you will get theta hat minus theta. Expected value is 1 over n. So you see that this 1 over n rate cannot be beaten even if you average everything. Essentially, you are kind of the statistical difficulty of the problem doesn't let you go below the rate that SGD has achieved. Okay? Now, okay, so just to give you some of the references that have proved these things, actually they proved much more than this. There is a paper by Chung in 1954. This is essentially 3-4 years after the original paper. And then another paper by Sachs, 1958. And essentially, in these two papers, they characterize everything, right? So they first showed that the upper bound I have, so I said that, you know, BT is upper bounded by, for example, if I choose alpha t 1 over t, this is going to be bounded by some constant over t. They showed that this is the exact rate. So it's not just upper bound, this is the exact rate. They also characterized the constant. That's what they did in their paper, and then they showed it's optimal. You can't beat it by any other algorithm. So this is 1958, right? Essentially, after that, people for a while had this idea that what else can we do with gradient, stochastic gradient descent? It's over, right? Everything has been solved now. Does it make sense? Any questions so far? Yeah. So the oracle, what is it supposed to do? It is supposed to give you an estimate of the gradient, right? The gradient of this one, so f of x, if I take the gradient of this function, this is what? This is going to be, this is going to be x plus, I think it's no. Okay, let me simplify this function. So f of x is 1/2 x squared plus, plus x theta. Actually, I should have put this one minus here so that I get what I wanted. X theta plus expected value of zeta t squared, theta 2 plus 1. So this is what f of x is. Then what is the gradient, or the gradient of f of x, let's say? It's going to be x minus theta. So the oracle is supposed to give you an unbiased estimate of this one. So what the oracle is going to give you is, for example, x1 minus zeta 1, x1 minus zeta 2, because this is now going to be an unbiased estimate of the gradient. Now you get the unbiased. So these are the information you got from the oracle. Does that make sense?
Oracle has access to a normal distribution.
Exactly. That's the assumption, yeah. Exactly. So that's what the oracle can do. But at the end of the day, the only new information that you have about theta is buried in Z1, Z2, the ZT. So that's why I'm assuming that I have these things, and I want to use these things to estimate theta. So that's how I assumed. Okay, so this is everything I mentioned is more or less about before 1958. So what did people do after that? And so as I mentioned before, so these are like, essentially everything became something that we can't do much theory anyway, because theoretically we know a stochastic gradient descent is optimal. So let's see what we can do practically, right? So the idea was that all these arguments So, yes.
Optimality is defined the same way.
That's a very good point. Optimality was defined in a statistical way here, the way we are going to define it in inference 2 in a statistics. So that's the way they tried to do the optimality before 1960. Around 1980, Nemirovsky and Yudin wrote a book, and they defined that model that I mentioned for gradient. And then they tried to prove optimality in that framework. Essentially, the idea is very much the same. So they proved it in that way too. And let me see if I have the references for the papers here, so that just in case you want to check. So if you want to read about that notion of optimality and a stochastic gradient descent, you can check the paper by Nemirovsky, the book by Nemirovsky and Yudin. It was written in 1983. And then a more recent version that they used a slightly different strategy to find lower bounds and then generalize it to other things. It is a paper by Agarwal. I think Martin Wainwright was on the paper. Ravi Kumar was on the paper, and I think Peter Bartlett. This is 2009 maybe, or 2010. I don't. But if you check it, you will find lower bounds for stochastic gradient descent. So you can check these papers for that framework. But before 60, it was very statistical. The lower bounds were statistical. Okay, so what were people doing after that? So theoretically, it seemed that there is nothing more to do on a stochastic gradient descent. So people started thinking about practical perspective, right? So, and then they started arguing that, one of the issues, so there are lots of issues practically with the stochastic gradient descent, right? The fact that you let the step sizes go to 0 very fast, that was the optimal rate, right? 1/t, the step size is going to 0 very fast. Asymptotically, we realize it's optimal for large values of t. This is the optimal thing to do. But then it makes the convergence rate reasonably slow, right? Asymptotically optimal, but still in the first iterations, the convergence rate is not going to be as fast as you want it to be, right? So then people said, what should we do, right? So we have to still improve the convergence rate. There are multiple directions that people were exploring in these years. For example, the first idea that people thought about was this thing, right? This is a natural idea. So you run, I would write averaging the iterates. So what was the idea here? I'm going to mention more about this idea. So you run a stochastic gradient descent, xt plus 1, xt minus alpha t, g, xt, and zeta t. So the issue that we had before was that, these xt is going to be a noisy version of x star, right? So this thing is always adding noise. Let's say if this is gradient of f of xt plus epsilon t, this epsilon t is a noise, right? So essentially, I have the iterations of the gradient descent plus alpha t noise. I know that the gradient descent is going to do well. We did the convergence analysis for it. It was good. The only issue that we have in the stochastic gradient descent is that there is this noise that we can't get rid of it, right? So what can we do? That's a very simple idea. We can say that, you know what? I'm going to take the average I from 1 to t, let's say. Why? Because now, let's say the algorithm has converged. So when the algorithm converges, the only thing that remains is noise, right? And we want the noise to vanish. So I take the average to make sure that the noise goes to 0. Does that make sense? So hopefully, this averaging that I'm doing is going to make the convergence better in some sense. Everyone is with me so far? The intuition is correct, but then you know that rigorously it doesn't give us anything because, at least it doesn't seem to give us anything because the stochastic gradient descent is already optimal. So far, so good? But I'm going to get back to this idea. This idea actually became very powerful because of the two papers. One of them is a paper by Robert, 88. And then there is another paper by Polyak in 91, I guess. And then another paper by Polyak and Juditsky in 92. And I'm going to get back to this idea because it's a very interesting idea, and you see that it gives us still something. The second idea is the idea that heavy ball method, we discussed it for gradient descent. So here it seems that if we take the averages of the gradients, it's going to help. So average the gradients or heavy ball methods. Methods. This is the second idea that people tried. You can imagine that the idea is something like this, right? Xt plus 1 is alpha t minus xt minus alpha t dt. And then dt is going to be beta dt minus 1 plus 1 minus beta g x t and zeta t, right? So now we are taking the average of the gradients to make sure that hopefully correct the direction of the gradient is going to help. Yes?
Average those x's. What would this x still?
So this is your estimate now. So this is going to be the estimate that you're going to output. So this is, it seems to be a better estimate. So if someone says, what is your estimate of the optimal, you're going to report this one, not xt. Xt is something that's running behind the scenes. That's the way they suggest it, but you can imagine that if you want to run it in practice, you would start from, for example, you will do t minus 50, for example, right? If you want to do it in practice. But theoretically speaking, yeah, you can start from 1 to the last one. Since most of the analysis was still and is still more or less asymptotic, you don't see the effect of starting from the first iteration. So that's why people write it in the papers in that way. But in practice, this is the way they do it. So the second one is, of course, the averaging the gradient, heavy ball method. Again, they had this idea for a while. I'm going to mention a little bit about it later on because it got more attention. Many people are using these things nowadays. And then, of course, the last idea that you can imagine people had, or at least have had, was kind of a closer to second order methods. If we have time, I may talk about it a bit. It's the idea of quasi-Newton methods, so closer to second order methods. For example, we can talk about quasi-Newton methods, and if we have time, I'm going to mention a bit about these things. So these are kind of the three directions that people were exploring, just to speed up the convergence rate and stuff. And then I want to explain each of these directions one by one to tell you what can be achieved theoretically and so on, and tell you some of the things that I think are open. At least I didn't find any paper explaining them, but maybe there's something and you will point to me later. Okay, so let's start the first idea, right? So the first idea was averaging the iterates, and this is a very nice idea. So I'm going to call it Rupert-Polyak algorithm. So I think people were doing averaging even before Rupert and Polyak. What is different in these two papers, they showed that it can theoretically give you some advantage, right? So that's one of the things they proved, and that's why people liked these two papers the best. So the idea is the following. What is the Rupert-Polyak paper? Again, you're running the same gradient descent that you were running before, g, x, t, zeta, t. So this is the classical gradient descent that we had before. But now I'm going to just report x tilde t. This is my estimate, which is going to be 1 over t, I from 1 to t, xi. Okay, they approach it in a different way. They said that, okay, I know that the stochastic gradient descent is optimal anyway, but if you want it to be optimal, you have to set alpha t to something like c over t, right? Some constant over t. And one thing that bothers people is that, you know, if you have this step size, which is 1 over t, and you change it a little bit and make it something like c over t to the power of alpha, all of a sudden you get an algorithm that's not optimal anymore. So it seems that your gradient descent, what does it imply? It says that the stochastic gradient descent is really sensitive to the choice of your step size. So if you choose something and then change it a little bit, all of a sudden you lose the optimality properties, right? So it's kind of sensitive to the step size. And the question that Rupert and Polyak were asking themselves was that, can we use these ideas to at least make sure that the stochastic gradient is not sensitive to the step size, right? And the idea was the following, right? The idea makes a lot of sense. The idea that they had, or the intuition that I think they had, was that if I choose larger step sizes, let's say I'm now taking c t to the power of 75. Instead of c over t to c over t that gives me the optimal one, I'm going to choose this step size, which is larger. So in the initial phases, it might be better than that one. Now, what is the problem happening with these things? It's just that the estimate that you're getting, so xt plus 1, xt minus alpha t, gradient of f of xt. So in this part, if you make alpha t large, it doesn't matter, right? Actually, gradient descent likes alpha t to be larger to have faster convergence. So what is the problem? The only problem that we have is in the noise. So if you make this one larger, it seems that you have larger noises, adding larger noises, right? So that's the issue that we have. However, now that I'm averaging, maybe I'm able to reduce the variance of these noises by averaging technique. And if I can, by averaging, I can reduce the noise, then maybe it works. Still, this algorithm is optimal, even though the alpha t is large. Everyone is with me so far? Makes sense, the intuition? So that's the intuition they had. And in fact, this is the theorem that Rupert proved. I'm going to modify the theorem because there was something that I didn't have time to think about it, so didn't have time to talk about it. So they said that suppose, so let's, this is from the Rupert 1988, and it is about the functions from R to R. The theorem was generalized by Polyak and Juditsky in 1992. So what he proved was that, okay, let's say now alpha t is dt minus gamma, and then gamma is now between 0.5 and 1. Then essentially expected value of x tilde t minus x star squared. Okay, I'm going to just write it something like this, 1 over t. So it means that it's growing like 1 over t. It's very much like a stochastic gradient descent. So this is like, let me emphasize what we are getting here, right? So I'm making the step size larger. It can be anything between 0.5 and 1. And just with this simple averaging technique, I could make the convergence rate the same as what you had in gradient descent, stochastic gradient descent, the optimal gradient descent. So the rate is the same as the optimal gradient descent. And in fact, even the constants, he proved that even the constants are the same as the optimal gradient descent, optimal SGD. That's what Rupert proved. I can tell you a little bit about the proof so that you can see what people were doing back from 50 to 80 when they were analyzing these algorithms, but it may take 10 minutes. I'm not sure if it's worth it. Okay, let's do it this way. I'm going to do a very fast proof, very hand-wavy proof actually, very hand-wavy fast proof, and it might not make much sense to some of you. If you don't like it, you can just not listen to me for 5 minutes. If you like it, you can just listen to me for 5 minutes, and I want to give you the idea so that you see where the trick was and why this was an interesting idea. At least on the result, at the surface, I think everyone agrees that it's an interesting result. But now let's see what was involved in the proof that people had to wait for, let's say, 20 years to get to these ideas, right? Okay. So let me just do a very, very fast proof. And this is a very hand-wavy fast proof. So I'm sure if the people who prove this thing see my presentation, they would be mad, right? They say that I'm simplifying their arguments. It's much more complicated, but that's fine. I think it gives the main ideas. Okay, so the first thing I do to make this thing very simple is that I'm going to focus on f to r to r, so one-dimensional function. And in fact, not only it's a one-dimensional function, it's going to be expected value of some number, some fixed number times x plus epsilon or zeta t squared. And divided by 1. So this is the function that we always play with, right? It's just if you want to know, if you take the expectation, it's going to be a squared x squared plus, and then zeta t is Gaussian 0, 1, let's say. So it's going to be this plus 1/2. And then if you write the stochastic gradient descent, you're going to get xt plus 1, xt minus alpha t, a squared x plus epsilon t. So this is what you would get from a stochastic gradient descent. And then if you simplify it a little bit, then you're going to see xt plus 1 is equal to 1 minus alpha t a squared xt minus alpha t epsilon t. That's again something we see. And then I'm going to do something that I did before. So I'm going to just write xt in terms of the same equation and then put it in. So eventually, what you will get is something like this. I from 1 to t, 1 minus alpha I a squared, x0. Now it's related. I'm relating it to x0 by these things. And then the difficult part, which makes it quite challenging, is alpha I, epsilon I, and then j from I plus 1 to t, 1 minus alpha I a squared, epsilon I. So if you want, you can check it at home. Let me make sure that I'm using the same notation I used in my notes, just in case I get confused later. So you can write it at home, right, to get this expression. And then for the moment, suppose that alpha I is some dt minus gamma, gamma between 0.5 and 1. Just gamma is not equal to 1, but that can be handled too. It's just that I don't want to make things more complicated. So, okay, let's think about this expression that I have, right? Let's first think about the first element, right? The first term. I have all these expressions, right? Let's say for most of the things that matter, alpha I is very small, so t is very large. So most of the i's, alpha I is going to be a very small number. So what I can do if I want to simplify this thing, I'm going to approximate this e to the power of minus alpha I a squared. So that's some approximation. Does it work? Yes, but you have to work it out, right? And that's what Robert did in his paper. So then what do you get? The first term is quite easy. So you get summation of alpha I a squared I from 1 to t. This is what you're getting. And now summation of alpha i's, so if it's 1 over I to the gamma, the summation of these things is going to be something like I to the power of 1 minus gamma, right? So it's going to be minus I to the power of, like essentially this summation, you can convert it to an integral, you're going to get something like this, minus t to the power of 1 minus gamma. So the bottom line is that this term is going to be extremely small, right? Because this is e to the power of minus t to the power of 1 minus gamma. Gamma is less than 1, so it's a really nice expression, and it's very small. So this term, really, when we talk about large T performance of the algorithm, this term doesn't matter. It moves away, it goes away, right? So the only thing I have to focus on is the second term. So that's the tricky term. And the nice thing that Robert did was essentially simplifying this expression, the second expression, and trying to show what it does, right? So the first thing, again, I can do the same approximation that I did before. So at least so far, we know that, based on my first argument, you can argue that, xt plus 1 is I from 1 to t, alpha I, j I plus 1 to t, 1 minus alpha I squared, alpha I a squared, epsilon I. So this is a good approximation. That's what I've said so far. And then again, I'm going to do some approximations. So again, alpha i's are going to be small. So let's assume that this is minus alpha I a squared again. The error that we are going to introduce is not large. So that's what proving these things is not, it's a lot of calculations, but it is more or less correct. And then again, I'm going to get something like this. I from 1 to t, alpha I, summation alpha I minus a squared, epsilon, sorry, j from I plus 1 to t. And now what should I do? I should essentially take the average. Let's say now what this algorithm is doing, t plus 1 to n, xt. So that is what we want to report, right? At the nth iteration, I'm going to report x tilde n, so I have to take this average. And then, okay, I'm going to put this in, so it's going to be 1 over n, t from 1 to n, summation I from 1 to t, alpha I, j from I plus 1 to t, alpha j, epsilon I. So now this is the time that magic should happen, right? So everything so far is quite trivial. What is the magic here? The magic is just switching the two summations, right? Of course, there's a lot to do, a lot more to do, but once you do this, at least something interesting happens, right? So if you switch the summations, you are going to get I from 1 to t, then alpha I and epsilon I are going to come out. Let me just make sure that I'm doing this is going to be 1 to n, and then t is going to be from I to n2, e minus a, summation alpha j from I plus 1 to t. Okay, So now the only thing that we have to do, these are A squareds. Now the only thing that we have to do is, which is not still obvious, is to show that this is somehow 1 over alpha I. So this summation that looks very not easy, that should be equal to 1 over alpha I. And okay, I'm going to stop here. If you are interested, you can ask me after the lecture. But this part is not too complicated, right? With a couple of approximations, you can show that this is essentially, I think, 1 over something like this, right? And then you will see that alpha is going to cancel out. So what you are getting is the average of epsilon i's, which is the IAD, let's say Gaussian. And the average, you know how it behaves. So that was the proof of essentially the Rupert, and this was the Rupert-Polyak algorithm. So this was essentially the first thing that showed, at least theoretically, all these heuristics that we have to improve the convergence of the stochastic gradient descent. We can say something theoretically about them too. And this was the first one. It showed that all the step sizes, or you can change the step sizes. So let me just mention again what the contribution was here, and then cite another paper, and then I move on. So the idea was that this is the Rupert-Polyak. This is the summary. It said xt is equal to xt minus alpha t the gradient. That is what we have here. And then x tilde t is going to be I from 1 to t, 1 over t, x I. And what they showed was that with any alpha t, for any gamma, alpha t, t to minus gamma, this algorithm is optimal. So it's much less sensitive to the step size compared to what you would get from the standard stochastic gradient descent. There was another paper that I wanted to mention a little bit about it, but I don't think I have enough time. Along the same lines, there is a paper from so like another question you can ask here is that, so still Rupert and Polyak algorithm requires the step size to go to 0 at these rates, right? So gamma, okay, for any gamma between 0.5 and 1, Rupert and Polyak said you have to set it this way. So at least still the step size should go to 0 very fast. And then there was this question that, can we make the performance of the algorithm more robust to this step size, right? Can I even talk about fixed step size and still do some changes to the output, some averaging, and show that still we can get reasonably good performance? And then there is this paper by Nemirovsky and Juditsky and the other co-authors, Nemirovsky, Juditsky, Lan, and Shapiro, that I think this paper appeared in 2009 or something. And what I suggest you check this paper. The calculations are quite easy compared to the calculation that was done, for example, in Rupert's paper or Polyak's paper, Polyak and Juditsky paper. The calculations here are very easy. And what they are essentially suggesting is that, they find, still they are going to do the same thing, xt minus alpha tg, xt and zeta t. but then they take a different average. So let's call it beta I. I'm very vague about these things, what they are. You can check it in the paper. Yeah, I guess it's better to. And what they can show here is that you can't get the optimal performance. You can't get the optimal performance with their strategy. But even if you have fixed step size and you know where you want to stop, you can still get something like expected value of x tilde t minus x star squared is less than 1 over some constant over square root t. So it essentially, this paper is suggesting that you can still increase the step size. You can still get fixed step size, and still the algorithm converges to the x star, not at the optimal rate anymore, but at a reasonable rate maybe. Okay, I can prove this one, but I think given the time, I want to move on to some of the other topics that are people are working on in a stochastic gradient descent. This one. So this very, very similar. Actually, maybe it doesn't take much time. Let me try to do this one. It's very fast. Okay. So how does it work?
What is the setting in which
This is true. So essentially, let's say the function is strongly convex again. The gradient is these things are unbiased estimates. It's just that beta i's depend on alpha i's. So they're not the same. They can be dependent on these things. But let me, I guess, do it because I left it very vague here. So, and this is another nice paper, I think. So let me try to mention more about it. Okay, so this is a very simple thing. So let's, okay, so this is what we have in gradient descent, right? xt plus 1 is xt minus alpha t gradient xt zeta t. So let's try to do the same calculation we did before, right? I'm going to subtract x star and then square both sides, right? So it's going to be expected value xt plus 1. Sorry. Yeah, that's fine. Minus x star squared. Expected value xt minus x star squared. Minus 2 alpha t. Expected value xt minus x star. And then this thing. Okay, this is the second term. And then alpha t squared, expected value g xt and zeta t squared. So I'm going to call, if you remember, we bounded this one by m. We assume that this is constant, so this is m. And then we also said that I can take the expected with respect to zeta t and take it inside. Everyone remember? So take the expected with respect to zeta t. So it's going to be gradient of f of xt. So we got the this thing that says xt minus x star squared minus 2 alpha t expected value xt minus x star gradient f of xt plus alpha t squared times m. Okay. Now here is the nice trick that, so this is a standard analysis of the stochastic gradient descent, right? So nothing fancy. But here is the a good idea that they try to do. So if you think about xt plus 1 minus x star, right? I can, what can we say? I can say that, you know, let's think about this one. So if I look at f of xt plus 1 minus f of x star, okay, so I'm going to do first order expansion, so gradient of f of x star and xt minus x star. So this is going to be, of course, 0, because the gradient at optimal is 0. And then you're going to get something like the second order expansion, right, in the Hessian part. And then you can say that, you know, since the Hessian is, we know that we have an upper bound on the Hessian, I'm going to have something like L here. Is it doing the thing that I want to do? Yes. Then I'm going to get xt minus x star squared. So this is going to be 0. Everyone is with me so far? So what does that mean? It means that I can just replace this one with f of xt plus 1 x star, right? So I'm going to just use, this is star 1, star 2, and then I say, so I'm going to say, I'm going to put a lower bound, so it's going to be f xt plus 1 minus f of x star is less than or equal to L times everything that I have here, right? So L, if you remember, I called this one AT, so L AT minus, we talked about, am I doing it right? Oh, actually, no, this is not the right way to do it. Sorry, I'm so sorry. So this is a t plus 1. So this is what we have. Let's actually do the same thing. A t plus 1 is less than a t minus 2 alpha t. Expected value xt minus x star. Gradient of f of xt plus alpha t squared m. So I'm going to take this one to the other side. So it's going to be 2 alpha t. Expected value xt minus x star. Gradient of f of xt is less than or equal to at minus at plus 1 plus alpha t squared times m. And now here is the cool thing that we have here. So we have what? If you think about this expression, it's the same as xt minus x star, gradient of f of xt minus gradient of f of x star. So again, I'm talking, let's say, because this is 0, I just add it here. So intuitively speaking, I can just pretend that this is the Hessian times xt minus x star, right? So, and then this is going to be what? This is going to be larger than the minimum eigenvalue, which is mu times xt minus x star. So this is what we get from here. 2 alpha t mu. Of course, this mean value theorem is not correct here. You have to do it with integrals, but it's fine, right? You can do the same thing. So 2 alpha t mu is going to be times x e. Am I doing it right here? I hope. Oh no, I have made so many mistakes here. Sorry. Okay, sorry. So far, so good. But then, okay, this one from the convex optimization, I know that this is even easier. So this is my function, this is the gradient, so this is this line. So it's going to be greater than f of xt to alpha t, f of xt minus f of x star. I guess that's the only extra trick, and I did it wrong 2 times. Okay, now what should we do here? Okay, so this is the trick, right? So we have 2. Now I'm going to take the average of these things, right? So if I take the average, 2t plus from 1 to t, alpha t, f of xt, then minus f of x star is less than, okay, so what remains here is a1 minus a t plus 1 plus or minus a t plus a t squared m. So if you add them up, both sides, most of these things are going to cancel out each other. And then I'm going to even drop this one. So I'm going to get a plus alpha t squared m. And then here is the nice thing. So this is the summation of alpha t f of xt. I'm going to just write it as, so this is going to be, so this is going to be larger than, because it's a convex function, it's going to be larger than f of t, okay, if I take the average, right, 1 over t, for example, you know, this is going to be some t here. So if I take the average, then what I would get is something like, oh, sorry. So if I divide it by summation of alpha i's, right, summation of alpha I from 1 to t, summation of alpha I from 1 to t, then you can see that I have the average of these functions, so it's going to be larger than 2 summation of f of summation of alpha I xi over summation of alpha i's minus f of x star times 2. This is less than or equal to a1 plus alpha t squared times m. So this is the way they define, this is I from 1 to t, I from 1 to t. This is the average that they define, right? So this is the average that Nemirovsky and Juditsky define. So this is going to be your x tilde t. So this is going to be f of x tilde t minus f of x star is going to be less than a1 alpha t squared m summation of alpha I. And now the cool thing is that you can even talk about, let's say alpha is a fixed number now. If alpha is a fixed number, you can see, so let's say alpha is fixed. So you can see that it's going to be, the upper bound is a1 plus alpha squared m n alpha squared, I hope. I hope that I haven't made many mistakes. Apparently I did. Exactly, so there is going to be another t here. Is that correct? I think so. At least that's what I've written here. And then you can optimize over alpha, right? And the optimal choice of alpha is going to be essentially alpha star is something like 1 over square root t. And then when you plug that in, you will see that the convergence rate becomes 1 over square root t, and that's what we get. So even with constant step size, if you know when you're going to stop the algorithm and then you tune the step size in this way, then you can get to 1 over square root t rate. Sorry that I got confused about the proof, but that's about it. So if you check it, you'll see that it's not very difficult. Okay, in the next 5 minutes, let me tell you a little bit about the other ideas that exist, and then we are going to stop. Okay, so as long as you care about f, that is correct. But if you want to talk about xt to x star, then you need that, and then you don't get the 1 over n rate, even if it's a strongly complex. So it's fixed. That's correct. Thank you. So this is one of the interesting papers. Now let's go back to the ideas that I mentioned before. The second idea that we had was the idea of heavy ball method. So these are the things that we talked about, averaging the iterates. This is the first idea that can improve the convergence rate of a stochastic gradient descent. Then the second one was averaging gradients and kind of the heavy ball idea. Heavy ball method. And then the third approach would be something that we may call quasi-Newton method type things. I don't think we can get to this one, but let's review a little bit of the second category. So the heavy ball methods have been very popular. I mean, and then many people propose different algorithms. If you want to go to some of the early proposals, you can look at the paper by Rudzinski and Siski in 1983, but I think even this one is not the first one who came up with these type of algorithms. But the thing is that since the theory of these things weren't that strong, and they didn't show that you get any improvement beyond the stochastic gradient descent, people didn't really like them that much. But then another paper that is probably very popular these days is the Adam algorithm, right? So it's kind of the heavy ball method, but with some better way of choosing the step sizes in the stochastic gradient descent, and then applied, of course, to deep nets, and then it's a very popular algorithm now. So if you want to see some of the references, you can check these papers. But on the theoretical side, still it's very open to see what these algorithms are offering to the stochastic gradient literature. For example, one question would be, do they help us in choosing the step size? Can they give us freedom for choosing the step size, like something that at least averaging the iterates does for us? And these things are, I think, open. At least I haven't seen, okay, to the best of my knowledge. My knowledge is very limited, so you can check the literature. If it's not correct, let me know. Just send me an email. But one thing that has happened, which is kind of nice, is another wave that kind of came out of this direction, right? And the idea was the following. So this is something that started in machine learning literature. So still, people wanted to see if averaging gradients can help or not, right? In general setting that we have worked on so far, we don't know if it benefits us, right? It's not clear. Then people started looking at a different set of problems, right? So for example, if you look at the machine learning problems, usually I said that we are talking about h of theta zi summation I from 1 to n, 1 over n. This was our function, right? So this is a very specific type of a stochastic gradient descent, right? Because these functions, at least I know the summation. It's in a summation form. Or in a more, if I want to write it in a slightly different way, I'm going to say that this is like a summation of some functions. Okay? And now the question would be the following, right? Okay, let me call this x to be consistent with what I have so far. Now the question would be, at least for these, if I want to apply stochastic gradient descent to these problems, it could be possible to improve the performance of a stochastic gradient descent by averaging the gradients, right? At least on this class of functions. We restrict the class of functions now, and then we ask the same question, right? Can, I guess it's me, sorry. I tried to not to go over time, but. So can we use gradient averaging to improve the performance of SGD? And it turns out that the answer is yes. Okay, on this class of a specific class of optimization problems. And the answer is yes. And I don't think we have time to talk about these algorithms, but you can check some of these papers. For example, 3 of the best known algorithms are SAG, SEGA, SVRG, and these are called the variance reduction algorithms. Usually they are called variance reduction algorithms, and the idea goes back to this idea that when I take the average of the gradients, I'm reducing the variances, and based on these things we can do better. I guess it may take time to go over these algorithms and especially say prove anything about them for now. So maybe we should stop here. Okay, thank you.